Hi, I'm Matthew Davison, and I'm presenting my paper, A Self-Sensing Haptic Actuator for Tactile Interaction with Physical Modeling Synthesis. This work was done by myself and Andrew McPherson from Imperial College London, along with Craig, Webb and Michele Ducceschi from the University of Bologna as well. So you've probably just heard a big plate crashing about 30 seconds ago. We're going to hear that again, but for slightly longer, as a little introduction to the research before we go into the technical bits. So here we go. So a bit of background on this research. Really the aim of the work is to create a system that can enable a rich haptic coupling between a performer and a physically modeled synthesizer. And this provides an initial platform for further instrument designs in the future. So there's many previous examples of DMIs with audio excitation of a resonant synthesis model using techniques such as Carr+Strong models and more complex versions. This technique provides the opportunity for rich control and avoids the sort of discretization that you get with MIDI synthesizers. However, the tactile element is usually unidirectional. So in effect, you're transferring tactile energy into the system, but there's no tactile energy returned from the synthesizer back to the musician. And any feedback that exists is solely auditory or possibly visual as well. So the system that I'm presenting today prevents a method of bidirectional tactile interaction with such DMIs, providing simultaneous tactile input and vibrotactile feedback with a single voice coil transducer. So let's have a look at the system goals. We want a bidirectional exchange of tactile energy and to enable a rich interaction through audio rate signals. And this bidirectionality, I'm going to say that a lot, and it's a very tough word to say, is achieved through three simultaneous modalities. Firstly, we're providing vibrotactile haptic feedback to the user's fingertip through this voice coil. Secondly, we're using it as a surface pickup for percussive excitation of the physical model through taps and hits. And finally, we're sensing the force applied to the transducer as well. And all three of these are achieved with a single voice coil transducer. So with bidirectionality, we run into a problem almost immediately, which is feedback loops. So the main issue with the addition of vibrotactile feedback to an exciter-resonator DMI system is the possibility of unstable feedback. If the transducer is driven by the output of the synthesizer, vibrations are picked up by the sensor and fed back to the input of the synthesizer, creating a feedback loop, similar to if I put this microphone right up against the speaker, which I won't demonstrate. And this can be mitigated if the transfer function between the actuator and the sensor is known, as the feedback can then be cancelled. This is quite difficult if you have a separate sensor and actuator because you've got a mechanical coupling between the two, which can be quite difficult to model. However, with a self-sensing system, we keep it in the electrical domain, which is then much easier to model. So to achieve this with a voice coil, we use the key feature that voice coil transducers are able to act as both a sensor or an actuator, one or the other. And this is quite a well-known attribute. So we've got here the Yamaha Subkick microphone, which is just a speaker woofer that they've put in a tom shell and said it's a microphone, which is used as a kick drum mic. Another notable feature is that the transducer's resonance changes with damping, which we'll come on to in a bit later as a nifty trick. But achieving both input and output functionality simultaneously is not so trivial and involves consideration of a voice coil transducer's impedance characteristics, which is basically just using Ohm's law. V equals IR is pretty key to this technique. It's a pretty classic electronics equation. I'm sure a lot of you are familiar. If you're not, it's just the voltage equals current times resistance. In our case, we're treating resistance as impedance because we're using AC audio signals. But let's just keep that in mind when you're looking at the rest of it. So with this in mind, let's go over the system design used in this research. So the single voice coil actuator is used as both a sensor and an actuator. So that's the actuator down in the bottom right there. And by actuating it with a current drive amplifier and measuring the voltage across the transducer as a sensing input, we know that due to Ohm's law, the transfer function between the actuation signal and the voltage sensing signal will be the impedance of the transducer. And then the voice coil's impedance is modeled with filters to cancel the feedback. Additionally, we can detect changes in impedance at a particular frequency, the voice coil's resonance, and use this to determine the amount of force applied to the transducer. So here's that in a fairly simple diagram here. We send in current, we've got an actuator with an impedance there that you can see on the graph, and we measure the voltage. So to form a digital filter equivalent of the transducer's impedance, we need to consider the various elements that contribute to the impedance in the first place. An equivalent electrical circuit model is a common approach used in loudspeaker design to characterize the electrical and mechanical elements of a transducer. You can see the circuit up there. And using this, the impedance can be found. So the first straightforward element is the resistance of the coil in the voice coil, which contributes to the impedance at DC. Then we've got the inductance of the voice coil, which contributes to the rise and high frequencies. And then we've got the mechanical elements. And these mechanical elements of damping, compliance, and moving mass form a resonant RLC circuit that creates this big old peak in the impedance of the voice coil. And changes to the mechanical damping value affect the peak level of the impedance spike, which is really the basis for the force sensing technique that we employ in this haptic system. So let's go into that in a bit more detail. So we can see the continuous pressure change applied to the voice coil here is detected through a change in impedance. So applying force upon the transducer varies the level of the impedance peak. And this graph here shows the undamped impedance, and it's got a clear resonance when we don't have our hand on it at all. Whereas this pink line, when we're pressing down with our hand, shows the impedance response with no resonance because we're effectively damping the actuator. And in between these two extremes, if you lightly press on it, we can get a continuous measurement of the force applied. And we can measure this change by adding just a constant low-level tone at the resonant frequency and effectively just measuring the level of that tone. Now, for the second function in the sensing domain, we use it to act as a pickup. So hitting the actuator produces an audio signal, which is fairly simple because it's effectively just a microphone at this point. However, we've also got an actuation signal. So it will act as a tactile pickup, and it's the same as a dynamic microphone. However, when we apply an actuation signal to the transducer simultaneously, the measured voltage becomes the total voltage, VT here, which is the actuation voltage plus any pickup voltage like the tap that we can see in these signals here. So basically what we want to do is remove that tap signal. So we can do this by taking the known actuation current, which is IA, and applying our filter model of the impedance to it to form an estimation of the actual voltage term. And this can be subtracted from VT, leaving only the pickup voltage, which we can see in the green at the very bottom, or almost see at the very bottom of the slide. So we've covered how the cancellation and the force sensing works, and just to go over the system design in a little bit more of a zoomed out view. Basically, along with the haptic system, there's a physical modeling synthesizer which runs on a computer, and that's created by our colleagues at the University of Bologna. The audio from the transducer feeds into the input of the physical model, with the force sensing parameter mapped to the damping parameter of these two modeled plates that you can just about see in the plug-in user interface there. These plates are activated by the signal from the transducer, which are then transmitted through the virtual metal surface and connections. Due to their strong non-linear nature, the coupling effects depend on the amplitude of the signal going into them. The plates are modeled using the Kirchhoff plate equation, which is a time-dependent partial differential equation that describes the relationship between the bending of the plate's surface and elastic force. This equation is solved using a modal approach, providing precise control over the resonant frequencies of the plates in real time. The nonlinear nature of the physical model is efficiently solved using the scalar auxiliary variable method that allows for efficient time updates. So that's the overall system. And before we move on to a quick summary, I'm just going to play that video again just to remind you of the system as a whole. So, to conclude, this research has shown a novel method of providing bidirectional tactile interaction between a human and a physical modeling system. The haptic system enables audio rate input and output and provides a platform from which further instrument designs can be developed. Thanks very much.